All right, so please share with your friends. Remind them of today's session. Let them know that we are now online and we are ready to start the session. We are in segment 2 of that performance-based assessment that we were looking at last week about the strand measurement. And so we want you to remind your friends that the session is on now. All right, so just waiting for a few more minutes for others to just rejoin us. All right, so we have other persons coming in. For the persons who are on with me now, just share with me if you were a part of our session last week, in which we completed segment 1 of the performance-based assessment entitled On the Farm. Sorry about my background, it's a little noisy at the moment, but just indicate in the chat if you were a part of that session last week. All right. So both persons were part of the session last week. So you are very familiar with what we did last week. So we're continuing. All right, so we are now at segment 2. And again, we apologize for the late start, having some technical difficulties there, but we're going to get right into it. So we're talking about costing and planning. So in this part of the task, as a part of his farm improvements, Mr. Clark plans to construct new feeding troughs and install feeding pipes for the pigs to improve feeding efficiency. With a limited budget, he must calculate the quantities of materials needed to estimate the total costs before starting the project. He is depending on your mathematical expertise to help him to make cost-effective decisions for the next phase of his development. All right, so going back to that part of the question, a feeding trough for the cow pen will be a triangular prism with the following internal dimensions: length 2.3 meters, width 0.2 meters, depth 0.4 meters. The external dimensions are length 2.5 meters, width 0.4 meters, and height 0.6 meters. Now we're asked to use the information to label the diagram that we're given. Can somebody explain to me why are we talking about internal dimensions and external dimensions? You can, if you'd like to speak, you can open your microphone. I'll allow you to speak. Raise your hand and I will allow you to speak. Why is it that we're talking about internal dimensions of the trough as opposed to external dimensions of the trough? Is there a difference between those two? Why are we distinguishing? Would anyone like to share? Why are we distinguishing between internal dimensions and external dimensions?
Thing in the chat, Mrs. Sims.
All right. What is happening in the chat, Dr. White?
I think they are thinking about it. Okay. Deidre Ray says the shape has inside and outside measurement.
All right. And that's exactly what we want to hear. And so the inside measurement, you can type in the chat, the inside measurement is referred to as which of the two? The measurements on the inside is referred to as which of the two measurements that we were talking about, internal or external? The measurements on the inside, you can type in the chat, right? On the inside.
Here it says internal.
Good, that's our internal measurement. And therefore the measurement on the outside is our external measurement. All right, thank you so much. So let's look at how we would label this diagram. Before we do that, let's identify our internal measurements. There are some key things that we want to highlight. The fact that we're dealing with a triangular prism, and we want to talk about the internal dimensions first. And we've looked at the length, the width, and the depth. So we're going to fill that information in. So the length, we're using that measurement as the internal length, and that's 2.3 meters. And the measurement at the top across there, we're using that as the width, and that is 0.2 meters. And of course, the depth of the internal depth is 0.4 meters. So that's our labeling for the internal measurements of the trough. And again, looking at the orientation of the trough, this is not your usual orientation for a triangular prism. It's not your usual orientation. In this case, we have flipped it upside down, so to speak. So we're looking at it from another orientation from what you're normally accustomed. All right. And now we're looking at the external measurements. So we would have already put in our internal measurements, and now we're looking at our external measurements. So let's put those in. All right, so we have our length, width, and depth representing our external measurements being displayed here. All right, so pay attention to those measurements. I'm sure you would have looked at the diagram. If your diagram looks similar to what I have here, can you raise your hands? If you would have labeled your diagram similarly to what I have here, please raise your hand. All right, Deidre, good.
Deidre, raise their hand.
All right. So I'm seeing both hands raised
as well, right?
Great. So that's what your diagram should look like. Very good. So continuing, can somebody tell me, because we're looking at two pictures here, one labeled A and the other labeled B. So you are part of last session. So you would have been exposed to some of these concepts already. So we just want you to share again your understanding of these two concepts. So it says, examine the picture to the left, define capacity and volume based on what you see in the picture. And therefore, we're going to ask you to state the difference between volume of the contents in the container and the capacity of the container. Who would like to share? I really would like for you to open microphone this time around and share. So let me know, Dr. White, who would like to share. Just raise your hands and Dr. White will identify you and allow you to speak.
Okay, I think they are thinking about it. No hand is up yet.
Okay. So we just want to know, when you look at those two pictures, we want you to be able to distinguish between volume and capacity. Share, we have two letters identifying the two figures. One is A, the other is B. Which would you say represents the capacity? And we're looking at it that both containers that are there are basically the same. All right. And so we're looking at which represents the idea or the concept of capacity and which represents the concept of volume.
Okay, Deidre says capacity is the maximum amount an object can hold, while volume is the amount of water in an object.
All right. So which of the pictures, tell me which of the letters A or B represents capacity and which represents volume?
Here says A is capacity and B is volume.
All right. Thank you so much. And so we have responses here. Thank you so much, Dr. White. And you are indeed correct. So we're going to need that information as we decide now to calculate. Let's go back because we are going to calculate the capacity of the trough. All right, so we want to recall that to calculate the volume of a prism, it's the area of the cross section, and we're going to multiply that by the height or the length, depending on how we refer to it based on its orientation. Can you share with me in the chat, when I talk about the cross section of the prism, what am I referring to? What does the cross section of the prism refer to? What am I talking about when I use the term cross section? Anything in the chat, Dr. Wayne?
Not yet. I know they are coming up with the response, but not as yet.
All right, so we're looking at a prism, and a prism is unique in such a way that it has something called a cross section. And so we want to find out from you, what does cross section refer to?
Okay, Desiree says the line between the triangle.
The line between the triangle. All right. All right. Could you offer some more clarity on that? I'm not sure what I think I need some more clarity on that, Deidre. Could you say some more?
All right. Pierre says the space between an object.
Space between an object. All right. All right. So we need to talk a little bit more about what cross-section refers to. So we're going to go back to our diagram. We're going back to our original diagram. And we're looking for the diagram that is on your paper. And so can you picture that this shape, this three-dimensional shape that I'm looking at, it's upturned. And so what shape am I looking at the face of the prism? The face that I can see along its length. What shape is it that I'm looking at along its length? Can you share that? What shape can I see along the entire length? And I'm seeing that shape at the front of the prism. What shape is that?
Nothing in the chat as yet.
Nothing in the chat as yet. All right. So we're giving them just a few more minutes to look at it.
Mm-hmm.
And so you just want to look, if you can imagine the prism turned upright, and we're looking at, so we have, how many faces do we have? We have one at the front, one at the back, two at the sides, and one at the base.
Okay, so Desiree says parallelogram.
Oh, it looks like a parallelogram to Desiree. All right. All right. So we want to look at, can you picture the prism turned upright? Think about that for me. If you are online, could you go to Google and look for the picture of an upright prism, triangular prism? Because remember, we said that the prism is triangular, and there's a reason it is called a triangular prism. So I'm giving you a second to ponder that. Why is this prism called a triangular prism? There's a reason for that.
All right, we are still waiting. I know they're thinking hard. Anybody would like to try? Somebody says not sure. Desiree says not sure. Are you seeing students? Mrs. Hales is holding the prism in her hand. I'm not sure. It's a little blurry, Mrs. Hales.
All right.
Yes, that's, oh, yeah, keep it right. Oops. Yeah, right there, right there. Gone again.
I'm
Right
not sure
there.
why it's blurry.
Yeah, right
Right.
there. It's
That's
okay now.
that's what the prism looks like. All right. So here is one face. What's the shape of this face that I'm pointing at? Anything in the chat? What's the shape of
Not
this
yet.
face? What's the shape of this face?
Triangle, says paired.
All right, so that's the one at the front. And there's a matching one at this side, at the back. Do we see that? And this is our prism. This is the length of our prism. And so when I look at my prism this way, I'm seeing a triangle. Turn it sideways. If I'm to cut along this length, this looks like a nice piece of cheese, doesn't it? And if I'm to slice a piece of this cheese for somebody, what shape, and I remove it, what shape would you see? If I'm to take a slice of this cheese off, cut off a slice, I'm cutting along the length, and I cut off a slice of this cheese. What shape will you see behind the slice that I've taken off? Anybody down?
Not yet. Okay, DJ Ray says triangle.
Right, and if I take another slice, still cutting along its length, cut off another slice, what shape will you see?
Pierre says triangle.
All right, so right along its length, if I'm to cut this prism right along the length, I'm always going to be seeing the shape of a triangle. And so that is why it is called a triangular prism. And this triangular prism, that shape that we continue to see as long as we cut it along its length is called its cross section. So what is the cross section of this triangular prism? What is the cross section? What is the shape of the cross section of this triangular prism?
All right, DJ Ray says triangle.
All right, great. So the cross section of this prism is a triangle. So we're going to go back to where we were, looking now at finding the capacity of this trough. And in finding the capacity of this trough, we need to find the volume of the prism. And to find the volume of the prism, we need to know the area of the cross section. And we're going to multiply that by either the height or the length. In our case, we're referring to that measurement as the length of the trough. All right. So we have identified that the shape of our cross section is a triangle. And likewise, we're looking at this representation of what that looks like. And so we know that the shape of our cross section is a triangle. And so here we are. We need to therefore find the area of our cross section. We recognize that our cross section is a triangle, and it came up before I got a chance to ask what is the formula that we use to calculate the area of a triangle. And because it's here, I will share. Of course, we use a half of the base multiplied by the height of the triangle. So can somebody share with me what is the measure of the base of the cross section? What is the measure of the base of the cross section of this triangular prism? What is the cross section of the base? Sorry, what is the length of the base of the cross section of this triangular prism? Looking at the diagram to the left, what is the length of the base? And we're looking at the internal measurements because, of course, the water is going to be thrown on the inside of the trough. And because it's going on the inside of the trough, we're looking at the capacity of what the amount that can hold on the inside of the trough. All right.
Okay, DJ Ray says the base is 0.4 meters.
the base of the cross section. Look at the diagram to the left again. Deidre, look at it again, because we have, of course, a measure for the height, which is, of course, in this case, the depth, because it's going down. So we have the depth and we have the length of the base of the cross section of the internal measurement.
Janelle Ray says the base is 0.2 meters.
Very good. So the base, the triangle is upside down. You see that? So the base is 0.2. And what is the depth or the height of this prism? The height of the cross section. So we know the base is 0.2. What is the height or the depth in our case?
All right. Deidre says the depth is 0.4, and so is Janelle Ray. I hope I said her name properly.
All right, great. So we can go ahead and fill in that information, and we already know the length of our prism. So we have the internal dimension, the length is 0.3, the width is 0.2, and the depth is 0.4. So in this case, the volume of our prism is going to be a half of the base multiplied by the depth. And of course, we're going to now multiply that by the length of the prism, which is 2.3 meters. All right, so calculating the volume, and we're talking about the internal volume, which is, of course, if it's filled all the way up, we're talking about its capacity, what it can hold, the maximum amount. And so the volume of that is going to give us 0.092 cubic meters. So I'm sure you would have had copies of this paper already, as I would have shared before. Can you let me know by the raising of your hand if this was a value you got for the capacity of the trough? 0.092 cubic meters. And of course, that is how it is read. Let me know, Dr. White, from the raising of hands, if
I'm not seeing any hand raisers yet.
We're able to get that calculated measurement. All right, so we know that the capacity of the trough is 0.092 cubic meters. How did we arrive at that? So in this case, we're looking at when the trough is filled all the way up. So in this case, its volume is equal to its capacity. And we're saying that the volume of a prism is found by multiplying the area of the cross section of the prism by the length of the prism. And so we would have had the dimensions, the internal dimensions of the trough. And we know that the base of the cross section is 0.2. And we know the depth of the cross section is 0.4. And these measurements are in meters. And we know that the length of the prism is 2.3 meters. So finding the product of these measurements will give us the volume of the prism. So the volume of this prism, which is equal to the capacity of the trough, is 0.092 cubic meters. So that answers part 2 of our question. So what about the thickness of the trough? How thick is the trough? What is that referring to? When we talk about the thickness of the trough, can you share with me, what do we mean when we talk about thickness of the trough? Would anyone like to share? What do we mean when we talk about the thickness of the trough?
They're thinking, but not yet. Okay, Deidre says density.
Density. That's interesting. Could you say some more? How can we arrive at, let me ask another question. How can we arrive at how can we determine the thickness of the trough? How thick it is? Is it thin? Will it break easily or so on? Or is the walls of the trough secure and thick? So this trough is sturdy so that it can hold the water without crumbling. That's what we're referring to. How do we know the thickness of the trough? All right, so we're going to look at our diagram again, and we're just going to highlight what we refer to as the thickness, how thick the trough is. All right, and how do we know? All right, so we identified that as our internal dimension, and we just found the capacity of that. And so that is the entire trough itself going across between internal and external. And so putting in the internal measurements, so we have our external measurements. So that's our external width, and we have our internal width, and we have our external length, and we have our internal length. And so in terms of the thickness, we're looking at what's that difference in space between the internal measurement and the external measurement. All right, so to find the thickness, it is of course going to be the difference between the length of the external and the internal width, as well as the external and internal length. And so when we find that difference, remember our external width is 0.4 meters, our internal width is 0.2 meters. So the difference between, when we talk about difference in mathematics here, we're talking about subtracting. So when I subtract, if you look at it, you notice these two arrows on either side. So it means that there's a space here and there's a space here. One on the right, there's space on the right, there's space on the left. When we talk about the difference, when we subtract these two measurements, we're getting 0.2. So the difference between the internal length and the external length is 0.2. Why are we dividing this measurement by 2? Can somebody share that with me? So we did the subtraction, but now we're dividing it by 2. Why are we doing that? Feel free to type in the chat. Why are we dividing this measurement by 2? That's it. So it came up a little fast, and so you would have seen it already. So it would not have made sense to ask some of the questions I had initially intended to ask. But the question I want to ask now is, now that you have seen this, and we are finding the thickness, and we're looking at the difference between the internal length and the external length, both length and width, and we're saying that the difference is 0.2, but we're dividing that measure by 2. When I subtract 0.2 from 0.4, I'm getting 0.2. But why is it that I'm dividing this measure by 2? Anybody? Share with me. I remember, we have a giveaway towards the end of the presentation. And so we're looking out for your participation so that you have a chance of winning this gift that we have coming up. So we're looking forward to your full participation.
DJ says because of the area of cross section.
The area. Remember, we're looking at lengths. So we know that one length is 0.4, the other is 0.2. So we decide to subtract them so we see what's the difference in length. So we got a value of 0.2. I'm asking, why is it that we divided that value again by 2? Why would it be necessary to divide that by 2 in order to find the thickness? Why are we dividing that value by 2? In the interest of time, we're looking at the fact that that difference is distributed on either side of the internal measurement. All right, so it's equally distributed because the distance between right around that space, that white space that we're seeing here, between both the internal and the external measurements, that space, they're actually equal. And so I need to find out what length is on this side, which is on the right side, and what length is on the left side. So it means that there's a thickness of 0.1 meters. So on either side of the internal measurement, there's a 0.1 meter difference that would result, if we were to add those two, it would result in the external length in addition to the internal length. I'm hoping that that makes sense to you. And so if I wanted to calculate the thickness using my external measures, what would I do? I would like to calculate the thickness of the trough using my external measurements. What would I do? Anything in the chat, Doc?
Not as yet.
What would I do? I would like to find the thickness using my external length and my internal length. What would I do? My external length, my internal length. I want to find the thickness. What would I do? Let me hear from our students. Let me hear from our students.
Still waiting to see a response. Okay, Desiree says subtract.
All right, tell me what I would subtract, Desiree. What would I subtract? Tell me what I should subtract from. Which measure should I subtract from which measure?
Or she says the internal from the external.
All right. So when I subtract, do that for me. When I subtract the internal measure from the external measure, what value do I have? When I subtract my internal measure from my external measure, what value do I have? So do that and let me know quickly. You are correct so far. We're going to subtract the internal measure from the external measure. What's the value that I have?
She says 0.2.
0.2. Now, is the thickness 0.2?
Meters.
All right, 0.2 meters. So are you saying the thickness is 0.2 meters? What do I have to do next now to find the thickness using those two measures?
Who says yes?
So I know that the difference in length is 0.2, but does it represent the thickness on either side of the internal measurement? Can I put 0.21 on the left side and 0.2 on the right side of the internal measurement? Is that what I'm supposed to do?
Okay, she says no.
What should I do? Still waiting. I have the 0.2 and I want to find out the thickness, but I know the thickness is going to be on either side of my internal measure. I got a value of 0.2. What do I do with that value? I'm sure it was already done using the internal and external width. And so we're repeating the same concept using the internal and external length. Anything in the chat, Doc?
He says subtract the 0.1 meters from 0.2 meters.
All right. All right. So basically what we're going to be doing is after we would have subtracted the internal and external length, we would have gotten those two measures in total. And so this measure of 0.2 has to be distributed evenly on either side of the internal length. All right. So we notice there's a space on either side of the internal length. And so we have to distribute that 0.2 evenly along that length. So if I'm going to distribute 0.2 evenly in two areas, what would I do? I'm distributing it evenly across two spaces. What should I do? I'm distributing 0.2 evenly across two spaces. What should I do? Evenly. And that's the operative word. I want to do it evenly, and I have two spaces that needs to get a piece of it. What do I do? Anything in the chat box?
Janelle Ray says divide by 2.
Divide by 2. Excellent. So that's what we're going to do. So we're just verifying either using the width measurement along the width or along the length that our thickness is consistently 0.1 meters all the way around, whether we check along its length or along its width. And I know the orientation here seems to be a little bit out of sync with the fact that we're actually dealing with a triangular aerial view. But nonetheless, of course, we're going to be distributing that 0.2 evenly across the two spaces. And thus to do that, we divide that measure by 2. And so whether we use the width or the length, we recognize that our thickness is 0.1 meters. Excellent. So therefore, continuing, we're asked, how much concrete will it take to make the trough? How much concrete will it take to make the trough? What are you thinking? Because we looked at the concepts of internal measure, external measure. We know that there's a thickness. So the concrete is going to be, that thickness is what is going to help the trough to be sturdy. So we know the internal measure, we know the external measure, and we want to know, let us say we were creating a mold to make this trough. So the mold is going to have the internal measure, and the thickness will be your space. And then we have another part of the mold on the outside with this, which is the external measure. So that's the external part. And of course, we have our internal part. So if we were to have, we have all of these dimensions and we can do our calculations for our internal volume, which is what we would have calculated in terms of the capacity, and our external volume, which we can also calculate. What would I do with these two measures that I have? That would give me an idea of the amount of concrete I'm going to need to pour into this mold to make the trough. Any ideas? I'm making a mold. This is your mold. And I'm going to be pouring my concrete in this space here. So around, not around, but within that space, internal borders, right? Where you see I'm moving my cursor. That's where we're going to pour the cement or the concrete into the mold. And we want to know how much concrete will I need to pour into this mold to make my trough.
Okay, Desiree says, find the difference between internal and external.
Excellent. Thank you so much. And of course, finding the difference implies that we're going to be subtracting. So we're going to be subtracting our internal volume from our external volume. And that will tell us the amount that we have in that, the volume of that little space that we have in between. All right, for which we had calculated the thickness. So we have our diagram already. We would have utilized this diagram already. And so our external volume, we can calculate because we have our dimensions, and our internal volume, we would have already calculated. And again, we said that we're going to be subtracting. And so for our external volume, it's going to be same formula that we would have used before, which is going to be a half of our base and depth of that cross section. And we're multiplying that by the length. And likewise for our internal volume, which we would have calculated already to be 0.092 cubic meters. So can you share with me then, what is the volume of concrete that we're going to need to pour into that trough? Work that out and give me your answer. You can type your answer in the chat. So we know our internal volume. We also know our external volume, and we are going to be subtracting our internal volume from our external volume in order to be able to find out the volume of concrete that we will need to make the trough using the mold that we have. All right. Any value in the chat yet, Doc?
Not as yet.
All right. So we're waiting.
They're thinking.
Right. We would have done that calculation already. And so we're just waiting now for the difference between these two measures to be typed in the chat. So we're waiting on those quick fingers to type, because you're going to need your quick fingers when we come to the giveaway. You know, we're coming up closely to the giveaway. So you're gonna need your quick fingers.
Okay, Janelle Ray says 0.208.
0.208. All right, so we're gonna check to see any other response just yet.
Deja Ray has the same response, but she added meter cubed.
Cubic meters. All right, thank you so much. So let's see. Did you say 0.208 cubic meters?
Yes.
All right, if you did, then you are indeed correct. Give yourselves a clap. Wonderful. Now, this concept is a concept that is not easily grasped. And so I'm happy to hear that you were able to identify what needs to be done in order to calculate this volume. All right, so I'm very proud of you for that. So continuing, so we're moving to the other part of the question, bearing in mind that we now know the amount, or we know the volume in cubic meters of cement that we will need in order to make this trough, right? So now we are told that if each cubic meters of concrete costs $8,500, and we know that we had 0.208 cubic meters of concrete that we will need, can you calculate the cost then to make the trough? Can you calculate the cost to make that trough? So we know the cost of the concrete. It costs it costs 8,500 per cubic meters. And we know that we have 0.208 cubic meters of concrete in order to, we need 0.208 cubic meters of concrete in order to make the trough. So it's really we're making the trough. All right. So what will it cost me to make the trough? Know the cost for the concrete and know how much I need. How do I calculate the cost to make the trough? Anything in the chat yet, Dr. White? How much money will it cost? Because you know when we're making anything at all, we have to calculate the cost. We have to count the cost. We have to know how much is this going to cost me? Can I afford to do this? And so we need to be able to tell Mr. Clark, we need to be able to figure out whether or not Mr. Clark will be able to afford to make this trough.
All right, Deja Ray says $1,768.
All right, how did you arrive at that figure, Deja Ray? What did you do? What operation did you perform? What operation did you perform to come up with that figure, Deja Ray? What did you do? How did you work it out is essentially what I'm asking.
Not sure.
How did you work that
she
out?
says multiplication.
All right, what did you multiply? Show your product in the chat. What did you multiply?
Okay, S. Thompson says multiply 0.208 times 8,500.
All right, sounds great. And so she got $1,768. So it would cost that amount of money to acquire the amount of concrete needed to make the trough. Great, thank you so much. And so here's the other part. On the farm, a pen for the bulls is a compound shape .
Are you there, Mrs. Hicks?
Sorry, I'm here.
Okay.
On the farm, a pen for the bulls is a compound shape made up of a rectangular and a semicircular section attached to one end. The dimensions are, I think this may be an arrow in terms of that part. There are some pipes. If we look back at our question, let's just read the question from the paper. So I think that might have been inserted in error. It says, Mr. Clark, plans to add cylindrical PVC feeding pipes in the pig pen. Each pipe is 1.2 meters long and 0.3 meters in diameter. He plans to paint the pipes to preserve and prevent it from hardening, because sometimes it's good to protect the pipes. So it says, calculate the surface area of the pipes to be painted if he wishes to paint 5 pipes. All right, so looking at that, so that's an example of the pipe and the water gushing down. And so our pipe looks like this in our drawing. So we're looking at finding the surface area, and we need to paint 5 pipes. So of course the paint is going to cover the surface area of the pipe. And what we do know is that, of course, that's a pipe, and the diameter of the pipe is 0.3 meters. And we would have discussed this in part 1. What's the relationship between the radius and the diameter of a circle? This would have been discussed at length in part 1. Can somebody share with me what's the relationship between the radius and the diameter of a circle? Can somebody share with me? What is the relationship between the radius and the diameter of a circle? Anything in the chat, Doc?
Not as yet.
So that would have been discussed extensively in our last session, where we talked about.
And Desiree says radius is half the diameter.
Radius is half the diameter. Excellent. Great. And so we know the diameter of the circle, of the pipe, and we also know that the pipe is 1.2 meters long. And Dr. White would have discussed this at length in our last segment. How do we find the surface area? What shape is this pipe that we're looking at here in blue? What 3-dimensional shape would you say this is? Give me the name of this 3-dimensional shape. Type it in the chat. The orientation may be different from what you're accustomed.
Okay, Desiree says cylinder.
It's cylindrical. Very good. It's a cylinder. And so we want to find the surface area of a cylinder. This would have been discussed in part 1 as well. All right. What do we do when we're finding the surface area of a cylinder? Bear in mind that this is a pipe. So when we look at the pipe, it looks something like this. This is a net of the cylinder. And of course, we're focused on looking at this cylinder having 2 closed ends. So the ends of the cylinder are closed. See those circles? That means that they're closed. All right. So we would have looked at in our last segment what it means to have both ends being closed, one end being closed, or we don't have any ends closed at all. And in the case of our pipe, we would have looked at this extensively in segment 1, where we made the relationship between the surface area, and we looked at the fact that the width of the rectangle is the same as the circumference of the circle. That would have been shared at length in our last segment. And so in the case of our pipe, we know that the circumference is going to be pi times the diameter. All right. And of course, that would have been shared at length in segment 1. And in the case of our pipe, do we have any of the ends of this cylinder being closed in respect of our pipe?
Mrs. Hayes, to answer your question that was asked before, DJ Ray says the area of the curved surface plus the area of the 2 circular cross sections.
All right, great. And so in the case of our pipe, because do we have any end of the pipe being open, or is both open, or is both closed in the case of our pipe? Because we want the water to flow freely. So what would we do? Would we have any closed ends on our pipe? Anything in the chat?
Not as yet.
We want the water to flow freely through the pipe. So would we have any of the ends of our pipe closed?
Okay, DJ Ray says 1 closed, 1 open.
All right, so if we close one end of our pipe, will water be able to flow freely through the pipe in order to get into the trough? If we close one end of the pipe, can water flow freely through the pipe?
All right, DJ Ray says no.
All right, so therefore, for our pipe, would we have any closed ends in the case of our pipe?
She says both open.
Both open. So what therefore would be the surface area of our pipe? Because the only surface we have now, we don't have any closed ends anymore. We only have what part of that pipe? The curved surface, which would be equivalent to what shape was used to form that curved surface. What shape was used to form that curved surface of our pipe? If we were to find the net of that curved surface of our pipe without the ends, what would that curved shape look like if we were to open it out in terms of its net? What shape would we see?
DJ Ray says a circle.
Not the ends. We're not talking about the ends now. So our pipe doesn't have any ends. So all we have is a curved surface of our pipe with both ends open. If I were to open out that curved surface, that net part of my pipe, if I were to slit it along its length and stretch it out, what shape would I see? I don't have any ends on it. If I slit it and just try to straighten it out, yes, cut it.
Okay,
along
DJ Ray
its
says a
pipe.
square.
All right, so I would accept that. It would either be a square or a rectangle, depending on the nature of the pipe that we're dealing with. And so that takes us back to the idea that our curved surface is really just going to be our rectangular shape that we have there. And we would have recognized that the width of the rectangle is going to be the same as the circumference of our circle. And therefore, the circumference, of course, we'd have discussed before, is pi times the diameter. So we know pi is 3.14, and our diameter, we were told, was 0.3. How do we use this bit of information? So remember now, from our previous segment, we would have said it's a curved surface plus the closed ends. But in this case, we don't have any closed ends because our pipe is open. So we are going to be focused on the curved surface. And so doing our calculations, how will we find the total surface area of our pipe? It's going to be 2 pi r h, or pi dh. All right. And so in doing our calculations, we would have identified that the width of our curved surface is going to be 0.942. That's just the width. And therefore, the total surface area of our pipe is going to be, of course, the width multiplied by the length, which gives us 1.13 square meters in this case, of course, because we are finding area. All right. So, of course, this aspect of it is very similar to what was done in part 1. And so the ideas are the same. And so if it is that we want to paint 5 pipes, and each pipe covers a surface area of each pipe has a surface area of 1.13 square meters, then it follows that if we're finding the surface area of 5 similar pipes, then we will have to, of course, multiply that by 5. So that gives us a total surface area of 5.65 square meters for our 5 pipes to be painted. And of course, if it costs us $900 per square meters to paint our pipes, and we know that for the 5 pipes, we have 5.65 square meters. Can someone share with me, how will I find the cost to paint these 5 pipes? I know that my 5 pipes covers a surface area of 5.65 square meters, and it costs $900 per square meter to paint these pipes. How will I calculate the cost to paint the pipes? Anything in the chat, Doc?
Not as yet.
I want to work out the cost to paint the pipes. I know that I have a surface area of 5.65 square meters to be painted, and it will cost me $900 per square meter to paint it. How will I determine the total cost to paint the 5 pipes? Share with me in the chat. Still waiting on your responses. It's very similar to what you would have done in previous parts of the question. So it's just to execute again in a similar way. I see something in the chat now.
All right, DJ Ray says 5.65 meters squared times 900.
All right. And what value did you get, Deidre? Did you work it out? Is your value similar to this $5,085?
Yes, she has that in the chat.
All right, great. Very good. All right, so we're in segment 3 now, where we're talking about time, speed, and delivery logistics. And here is our question. Mr. Clark gets water from a treatment plant 12.5 kilometers away. If a truck travels at an average speed of 50 kilometers per hour, how long will it take the truck to reach the farm? Did anyone answer this part of the question before? Mr. Clark gets water from a treatment plant 12.5 kilometers away. If a truck travels at an average speed of 50 kilometers per hour, how long will it take a truck to reach the farm? So, of course, we have to highlight the most important items here in our question. And of course, we know the distance is 12.5 meters away. And we're looking at an average speed of 50 kilometers per hour. And what does an average speed of 50 kilometers per hour mean? Can somebody tell me what it means to be traveling at 50 kilometers per hour? Can you explain that for me? You can type in the chat, or you can raise your hand and we will open mic for you. When we say we're traveling at an average speed of 50 kilometers per hour, what are we talking about? You're saying that? Okay. We're going 50 kilometers per hour. 50 kilometers per hour. What does that mean?
DJ Ray says the kilometers you travel per hour.
Very good. So for every hour, you're covering 50 kilometers. And so we need to travel a total distance of 12.5 kilometers. So if we revise carefully what we're talking about in terms of distance, speed, and time, looking at this picture that we have here, we can see that speed can be determined by dividing the distance by the time, and distance can be determined by multiplying the speed by the time, and time can be determined by dividing the distance by the speed. So in our case, which of these are we finding? Because we are asked, how long will it take in minutes to arrive? How long? So we talk about how long, and we talk about in minutes. Which of these are we referring to? Speed, distance, or time? What are you saying in the chat? The question is, right, the question is, how long will it take in minutes? I think that's a clue. Are we finding, therefore, speed, distance, or time? Which of these can be measured in minutes? Anything in the chat?
Not as yet. All right. DJ Ray says time.
Time, excellent. So in order to find time, we're going to be doing what? How will we utilize the information that we have to calculate the time? What will we do? We know how far away it is, so we know the distance, and we know how fast we're traveling. Our average speed is 50 kilometers per hour. How can I use those 2 bits of information to calculate the time? We know the distance, we know the speed. We know the speed, we are given the distance. How will we calculate the time?
Okay, DJ Ray says distance divided by speed.
All right, distance divided by speed. We know the speed and we know the distance. Very good. So it's distance divided by speed. Go ahead and tell me what is the time in minutes. Give me that time in minutes. So you know the distance, 12.5 kilometers. We know the speed, 50 kilometers per hour. Please give me the time in minutes. Anything in the chat? We just said distance divided by speed. What did you get? What value do you have when you divide distance by speed? Waiting on your value. Distance divided by speed. What value did you get? Give me the value that you got. If you're not able to interpret it yet, that's fine, but tell me the value you got.
Okay, Desiree says 4 minutes.
4 minutes. All right. What value did you get when you divided 12.5 by 50? What value did you get? You can type that value in the chat.
Smith says 0.25.
All right. 0.25 is correct. But how do we interpret this now in terms of time? Because we divided by 0.25, we know the speed is kilometers per hour. So 0.25 refers to what? Could I have 0.25 as a common fraction? What's 0.25 as a common fraction? Because that's going to be a fraction of an hour. We have it as a decimal fraction as 0.25. If I wanted to write it as a fraction with a numerator and a denominator, how would I write that?
Desiree says a quarter.
A quarter. So it's going to be a quarter of an hour. And how many minutes are in a quarter of an hour? How many minutes do we have in a quarter of an hour? How many minutes are there?
Desiree says 15.
15 minutes. Great. So it's going to take the truck 15 minutes one way to get to the farm. One-way travel. All right. Excellent. Give yourselves a hand. Wonderful. I'm so proud of your participation, and I'm sure you would have gotten a chance to work through the paper. And I'm sure that wherever you got stuck, or if there were any challenges that you faced, that you would be here now to get your clarity. And I'm hoping that that clarity has been given to you. All right. So just before we go, don't leave. Just before we go, we have an activity. You're going to get a chance to win something. You're going to get a chance to win a $500 Flow credit. So if you have a Flow phone number and you wish to win a $500 phone credit, I'm going to flash this across the screen. It's going to play momentarily. Let's go back. And if you can type in the chat what is written there, exactly what is written there, behind those yellow circles, the first person to type that in the chat, you will win yourself a $500 Flow phone credit, and you will have to then share your telephone number with us in the chat so that we can top up your Flow phone with that credit. All right, if you're ready to begin, raise your hand. You ready? Raise your hand so I can see that you're ready to begin. And so I'm going to post that again.
All right.
First
Desiree hand is raised.
All right, the first person to type what is there in the chat, you're getting a chance to win $500 phone credit. And it's not going to stay there forever. So let's go. All right, I'm counting. Yeah, you have to type what's there in the chat. All right, that's it. One more time, and that's it. All right, anything in the chat, Doc?
Not as yet.
Anything in the chat?
Still waiting.
All right, let's see who types it first. You're getting a chance to win a $500 phone credit from Flow. All right. Are we going to have to end the webinar, Dr. White, without a winner?
That's what I'm wondering.
Are we going to be ending without a winner?
We need somebody to take this credit.
Yes, we absolutely need somebody to type in the chat what was there so that you can win yourself $500 worth of Flow credit. All right. It's not a hoax. We're waiting on your telephone number as long as you type it correctly. We're waiting on your telephone number so that we can give you that $500 Flow credit. You know many things you can do with a $500 Flow credit, though?
I'm telling you.
This is like gold. There's so much that can be
All
done.
right, here comes Deja Ray.
All
And she
right,
says,
Teresa.
there are 5 strands in mathematics. These are algebra, geometry, measurement, trigonometry, and number theory.
All right, DJ, you got it. Congratulations. All right, congratulations. You are the winner for $500 flow credit. Please type your number in the chat or send your, I'm going to write my email address and you send your number to this email address. All right. So isn't this wonderful, Doc?
Wonderful. Good participation. They did so well.
Yes. All right. All right, DJ. So I'm sending you my email address. That's my ministry's email address. So I'm sending you my email address. And that's janice.simpson-hales@moey.gov.jm. You're going to share your telephone number in that email so that I can send you your credit. All right. Thank you again. Thank you so much for your full participation, everybody. And that brings us to the end of our task-based assessment review. I'm hoping that you would have found the sessions useful because this is something new that we are trying to incorporate across the region to have our students doing more task-based assessments. Thanks again for your participation and see you again next time when we hope to have a similar session next year. Take care, everybody. Thanks again.